So as I'm getting myself set up and I'm in the VS Code terminal, and by the way, you can have more than one terminal, and you can see how many terminals you have open over here. I don't need two different terminals at the moment, so I'm gonna get rid of more than one terminal window. I'll just create a file named notes.md, and let's take a look at it. So the big question, what is a database? We're gonna talk about the structured query language. I said standard query language the other day, which was not quite right. And actually, you know, this breaking down language exercise is really good. With SQL, can someone tell me, why do we call it structured? Why is it a structured query language? And let me look in the chat.
Is it because order matters? I don't really know.
Great guess. You're on the right path. Order does matter. I actually would probably have to Google this to get the exact answer, but I'm going to run with because our data is structured. And like with all programming languages, order does matter. And actually, let me make sure I have the SQL acronym right. Yep, structured query language. So I was saying standard query language the other day. Yeah, really, I think the answer is because the data is structured, but I might come back to that. Query, why query? What does that mean in this context here?
Well, it's pulling the data from the database.
Yeah, exactly. We're going to query a whole bunch of data and just get the parts that we're interested in, which people have been asking about with APIs, and is a good question, and is you can't quite do, right? And then language, what kind of language is SQL? So that's a good call, a query language. I could see that. There's not like a right answer here. It's a programming language, but the term that you'll see is like domain specific language. And a domain is just some area of computing or the business world or anything else, like cars could be a domain. In this case, relational databases are a domain. And this happens all the time where like a problem is, or a space is complex enough where we want to basically construct our own highly specialized programming language for working with a very particular kind of problem or space. And in this case, a programming language that we can use to make queries for a certain kind of database. And this sounds like a little bit of a silly question, but it's actually, I think, going to open some really interesting doors. What is a database? If we all had technical interviews tomorrow and the interviewer said, what is a database? What would you say?
An organized collection of information.
I love it. What else is a database? Base of data, records. So if I go ahead and I create, let's see here. Let's say I create a directory named data. And now over here, we've got this directory named data. Let's say I'm just going to use the touch command to create in the data directory a JSON file that has some sort of name that's some sort of unique ID. And I'm borrowing from the curriculum here up on GitHub. And someone remind me, what is a JSON? What is JSON when I'm talking about JSON and a JSON file? Because we've talked about that a little bit, but probably not a ton. So what is JSON?
JavaScript object notation.
Totally. And what does that mean?
It's the format in which the data is being stored.
Yeah, exactly. Like this looks a lot like a JavaScript object. JSON is a format for a text file, just the same way that HTML is a format for a text file, or .md, Markdown, is a format for a text file. This format borrows the syntax from the JavaScript language of objects, because it turns out it's very useful. And by the way, like if you want to check it out, it actually is pretty interesting. Like JSON has its own rules and specifications of what a JSON file can and can't include. The biggest gotcha being a JSON file cannot have a trailing comma for the last item for the last attribute on an object, or the last item in a list, in an array. JSON does not like that. In JavaScript, that's okay. But it's a structured format for storing information in a text file. So now I've got in my file system a directory named data, and I have a JSON file. Is this a database? And I've got data in that JSON file.
I'm going to say yeah.
Cool. What else? What do other people think? I think I need to think about this a bit too. I'm trending a little bit towards no, but I'm not 100% to be honest, and we're going to talk about it. Why is it a database?
Because it's an organized collection of information in a file.
That's true. That's very true. But then what about this markdown file? Is this notes.md file a database? This is an organized, structured collection of information. There are plenty of Python libraries out there that know how to parse markdown files. VS Code can understand this. Is notes.md also a database?
No.
Yeah, I would argue
Maybe.
no. Maybe. Yeah, I haven't looked this up. A JSON document database. Yeah, so Kayla, yeah, you're kind of going in an interesting direction in the chat, and Jim, you are as well. And I think where this is going is like, how do we store information? Where do we store it? The file system is not a database. And actually, I should Google that, because now that I thought about it, I never thought about, is a file system a database? Let's find out. So this is a great question. What is the difference between the file system and a database? I like this description of a file system right here. It's unstructured data. Traditionally, a file system like mapped very directly to the actual hard disk of a computer. A database doesn't necessarily have any relationship to like the hard disk of a computer. So we have a higher level of abstraction. There's a lot of other stuff here that's going on. Like, I mean, as you can see, this is kind of like a 6 of one, half dozen of the other kind of question. I think that some of the big differences are is about storing files on the hard drive. What I would say is a database is a program in which we store data. A database provides a layer of abstraction higher than a file system, generally speaking. To go back to this JSON example, maybe I write a Python program that can grab this JSON and do stuff with it. And with my Python program, I can create new JSON files with new students and new classes. Maybe I create a database program in Python, and maybe the way that my database program stores information is in these JSON files. But then when I write another program to use that database, I don't have to know how that database like internally stores its information. When we use a database, we don't have to worry about database internals, generally speaking. And I'm curious what people think about this, if this is an interesting distinction to make, or if this feels a little abstract and people are wondering like, why is this relevant to stuff? So I'm going to take that as mostly positive and kind of keep on rolling. To recap, to kind of go back to this JSON file, I think one really important distinction to make is, and Jim, you mentioned a record. That's a really good term too. Like, we are going to start giving ourselves abstractions to think about that information, and then how we actually store that information might be different. Let's see. I think I've probably talked enough about the JSON file. And I think I want to talk a little bit about relational databases now. So our problem is we have large quantities of information. We have records or entities or things. There are relationships between those things. And let me and here, just to make the distinction, I'm talking about a class as in a class you take in school, not like a class as an object-oriented programming. So to use this school example, to look at this JSON file, it's great that we have this information structured here. There are many ways we might want to query this information. What if I want to get a list of all the students in the CS 101 class? Well, if every single one of my files and let me go ahead and very quickly copy it so we can look at two together. I don't know here. We're just going to do 5, 3. And let's clean it up a bit. And we don't need the terminal for the moment, so let me get rid of that. So maybe we have, I'm being very lazy and I'm saying maybe we have twins because they have the same birthday and they live at the same place and they have the same last name. And that's actually a great example of an edge case when you're thinking about like structuring data and databases and stuff. And they're taking almost the same classes, but slightly different ones. And as we know from writing programs, the structure of our data really shapes how we can query it. You know, I think you all can start to think about if I said like, give me a list of all the addresses of all the students, and we had a bunch of JSON files that looked like this, how you might do that. If we had to get a list of all the classes that the school has, or all the students that attend a class, like that, those are non-trivial operations. And depending on the structure of our data, like there's very different ways of doing that. And the truth is that like when we're writing programs, it'd be nice if we didn't have to do all that work from scratch every time. And the idea of a relational database is that a relational database is used to create relationships. We call them tables. And I'll talk about that more in a sec. It looks a lot like a spreadsheet. But what we're seeing here is these are our things. Maybe it's called a record. Maybe it's called an entity. Maybe it's called a table. If we were writing code, there might be a teacher class, but we have this concept of a student and a teacher and a school when we're modeling our domain. And then there are all these relationships. And this just shows up everywhere. It's not just with school. What's another domain that might be interesting for us to talk about relationships with? It could be like a company payroll. It could be a video store, which is one of the exercises that we're doing. Someone give me something that we can use and talk about the different like entities and relationships inside it. Not a trick question.
A movie theater that's showing different movies and has different screening rooms and different employees.
Yeah, I love it. A movie has theaters, or let's say screening rooms, and it has employees. What else does a movie theater have?
Different prices for time of day.
Yeah, that is a really good point. I have to think about that one. Has price, different price at different, what should we call it? Like screening time?
So maybe like a regular price and what is it, a matinee price?
A regular price or matinee price? Yeah, let's say like has showings, regular, and matinee. And for showings, it's really as movies, and let's say movies have showings. Like it has showings. I should put that there. But I think this is where the power of relationships starts to come into play. Like it's really hard to talk about a showing without thinking about a movie. And yeah, seat selection, that's a great point. Has seats, and we would say like a screening room, which is probably not the best term. We could call it a theater. Do people have strong feelings about one or the other? Sticky floors equals true. Discount prices based on age. That's a great point. Prices based on age. How to model. And I actually have to think about how we want to model that one. Screening rooms have seats. Memberships, that's a great point. Like we've got customers, and then we've got memberships. I'll just put over here like customers have memberships, and not all customers are going to be members, but some will. So we have just a lot of different relationships. Sticky floors, the concession stand, that's an excellent point. Concession, and then like maybe concession has inventory. And that actually is a good point of where we have to decide too what the limits are of the world that we want to model, because just modeling, like writing out the different things in a concession stand and how to track that is a whole operation. This is awesome. This is great. And like prices based on age, that's a really good point. I think it has to look somewhat similar to how we did like different kinds of showings. So like, what is it? A showing. Well, this is where it gets interesting, like a regular showing, a matinee showing. Showing has price. How did movies have showings? Regular and matinee. So let's see, price, regular and kids and senior discounts. And there could be many more like categories. And again, it depends on how we want to model it. So it turns out that this basic idea of relationships is really powerful. And that's what a relational database is. It models things with, we call them tables, and then relationships between those tables. I'm going to see if I can find a nice diagram. Yeah, that's not the best diagram, but you can kind of get the idea. And in fact, let me see, I do have this drawing program. Let's see if we can maybe start modeling our movie theater in our drawing program. This is not going to be the best way to do this. Let's see, we said we had a screening. And I'm going to refer back to our notes. Screening room, employees, showings have price, movies have showings. So movies, showings, price, screening room. I think that's a good start. A movie. The screening room. And in fact, we might just need, and then I'm not sure if movie and showing is redundant, so I think I'll just leave that there. And then let's say we have price. And then we have these relationships, right? A movie has a screening room. A movie has a price. A screening room has a seat. And then if we have a customer, they're going to have a seat as well. And we haven't even started to think about like what's inside of these things yet, but just even at a very high level, we can start to think about like the different entities that we have and the different relationships between them. And actually, this is probably a great point to start writing some SQL code, and we can probably just create this database. I think, let me see if there's anything in particular that we should talk about with like relational databases at a high level, but I feel like we're actually covering things pretty well. And actually, I think what I'll do is we have a nice little slide deck that kind of goes over the structured query language. So SQL is a domain-specific language for working with relational databases. And before diving into that slide deck, let me see if folks have any questions or things on people's minds. And if I've been missing anything in the chat, I apologize. Awesome. And I think what we'll do, and I think the best way to do this is I'll go through this slide deck and talk about it and ask questions, and then we'll take a break, and then we'll actually build our movie database. And you folks can just kind of watch me write some code and some SQL and do that. The other piece of context here, I think that probably is important, is that a database, as I mentioned, is its own program, its own piece of software. We're going to be using a database called Postgres, which is a relational database, which, as we now understand, like relational means these relationships between these different entities. And in a relational database, the term that we usually use to talk about these entities is a table. And like we were talking about here, when we're interacting with our database program, we don't have to worry about what format our database stores things internally, how it stores things in a file system. That's abstracted away. Other things very quickly that a relational database, that just a database does for us. Scale. If our website makes thousands of requests a second to the database program can handle that load. And it depends on the kind of database, but guarantees about data consistency. Like with the JSON file, if I screw something up or I put data in there, or I don't know necessarily that this class even exists in another file, relational databases in particular give us guarantees. And we don't touch on it a ton, but specifically the term is ACID. Let's find a good. Wikipedia is never a bad one here. But this is a good example of transferring funds. If I use the internet to move money from one bank account to another, however it happens, when the bank moves money, numbers are getting moved around in a database. If something goes wrong in that process, we need to know, like the money either needs to be moved successfully or not. And so databases can be very strict around guaranteeing that certain transactions, whether it's a transaction with money or a transaction in a more abstract sense of maybe adding a new user account, that those transactions actually happen, or if they don't, the database complains and lets us know. So that's a big advantage. The same way that when we all have been writing like maybe logic to check for errors in our code or raise errors, databases do a lot of that for us. And I think for the moment, I will just throw the Wikipedia link there because it's not as directly relevant, and I want to get us started on actually doing some stuff with SQL and databases. Oh, I did want to share the other thing I think to talk about at a high level for a database, and I think this image might be a good one. Let's see. Yeah, perfect. So we are running a database program on our computer. The kind of database program that we're running, like, is really designed to run on its own computer these days in the cloud. And we haven't talked a lot about web application architecture. We can ignore all this stuff. All this stuff up here is the internet. Where it starts to matter is this idea that, like, here I've got a server running Django, another server running Django, another server running Django. And my website is Nordstrom's. So tens of thousands of people are looking at it at the same time. And we have another server here distributing those requests among these servers. Maybe we have some images that live in a file system, but then most of the data about what you can buy at Nordstroms.com lives in a database. And this database program is really designed to run on its own computer and handle a very high volume of requests. So I think that's the other piece of the puzzle that's good to know. Like, I'm going to be using this database Postgres on my local computer, as you all will be. But these tools are also designed to be used in like larger systems and application architectures. Sebastian, that's a great question about how do you set up a computer explicitly for a database. It's a little outside the scope of this class, but essentially the answer is you would probably do a lot of stuff at the operating system level. Like, you would just not install a lot of things. Like, you also would buy a very specific piece of hardware if you wanted to like have a server computer be a database that was really going to handle a high volume. You don't actually have to do a ton to get it going. At the end of the day, you can stick a database on any computer and expose a port, and then there's access to it. But yeah, Jim, essentially you have like a dedicated machine or virtual machine. Many of you may also have heard of a database called MySQL. It's another relational database, very similar to Postgres. I kind of feel like Postgres is a better piece of technology in some ways, or at least I'm more familiar with it. They're both very common. They're both good at different things. And one interesting thing to note is Postgres is an open source database, which means if I go somewhere on GitHub, the entire source code of Postgres is there for me to see and available for me to use under some kind of open source license. I don't think MySQL is open source these days. They might have an open source version, but you have to pay for it. And I think, in fact, when we Googled MySQL, we saw Microsoft Azure. So Azure is Microsoft's cloud service, and they have their own MySQL, and Amazon Web Services has their own relational database, all of which use SQL. So actually, I'm going to take that to run here. So I'm going to kind of walk through a bit of SQL, and we can take a break. Let me check in with folks, though. Do we want to take a 5-minute break now before we go through this? Because I have been doing a lot of talking. How are people feeling? Is that thumbs up on the break or thumbs up on the let's keep rolling?
Keep
Okay,
rolling.
we're going to roll. So this is great, right? We've talked about tables. We're looking at a products table right here. The table has fields. It's exactly like a spreadsheet. To just kind of drive the analogy home, let's see, product, product ID, name, price. So I don't know where this lives, but we've got a product table. It has these 3 fields: product, name, and price. And then we can give them values. And the whole thing does work a lot like a spreadsheet. And we can see we've got a product table. We've got the relationships that we talked about. And we'll talk more about this later. But the essential thing to know is that the way you define a relationship is you have to say, this is the unique ID that helps you find a record for this table, a row in this table. Over here, product ID is our unique ID. This order line, the order of products, I guess, is related to the products table by the product ID. So we have this other table that has a product ID in it. And I think probably customer and order is a bit easier to understand. If you create an order, we need to know what customer made that order. So the order table will have a field named customer ID, and we can then use that to go look up a customer. And this part of the slide over here isn't really relevant. Essentially, there are non-relational databases. They have their value. We will not be using them or discussing them too much in this class. So as we talked about, a big advantage of a database is it abstracts away a lot of the work of how is this data saved in the file system, maintaining integrity with the data, and things like that. So really, with a relational database, we need to understand tables, columns, and rows. Columns and fields I will use interchangeably. And in fact, I probably didn't do this very well because it should look like that and should be like this. I did this terribly wrong, in fact. So we've got our table, we've got the product ID column, the name column, the price column, and then each row actually contains all the information for a product. And again, the spreadsheet metaphor and using a spreadsheet is a really good way to visualize this stuff. And then we have the structured query language that we use. And so exactly like you can see here, like we're going to build our movie theater in a bit, but here you would have a students table. The ID is kind of the critical part because it uniquely identifies the student, and then we can add columns to our students table. So a schema is the term for essentially the blueprint of our database. It would include all the different tables, their names, the names of all the columns, and then the types. To go back here, when we create this first name column, we would probably declare that that column has to contain strings, because a student's name is not going to have an integer, and we don't want that in our database. And that's one of the big advantages of relational databases too, is being able to declare types for columns. The SQL syntax is pretty straightforward. I'm not going to spend too much time on these slides because we're going to just start doing them in a little bit. This really, I just kind of want to give a flavor for what SQL looks like. And there are a couple different ways to write SQL. Let's see, going back to our movie theater, we had screening rooms, we had employees, we had showings. Let's create an SQL file for screening room. I actually have to look at my syntax here. So I'm not sure how helpful, we'll see how helpful Visual Studio Code is. What are some other columns that we probably want our screening room table to have if we're building up like a model of a movie theater?
Size, capacity.
Capacity, yeah. And that's number of seats.
Yes.
Maybe a name.
Yeah, I like it. What else?
What movies
Size.
are showing?
I'm sorry.
What movies are showing?
Yep. Do we want to know what movie is currently playing there, or what are you thinking?
We could call it a schedule, and it would be
A
like a list
schedule.
of movies that it's showing that day.
Yep,
Is
totally.
it handicapped accessible?
Handicapped accessible.
Depending on how detailed you wanted to go, you could have screen type and or sound type.
Yeah, I like that. Screen type. And I shouldn't use string because that's not quite correct. Let's see here, Postgres, string types. So there's three different ways. This is where the advantage of a relational database is it lets us get more specific, but it also means there's a bit more. Like, for example, maybe we don't want the name of the screening room to be too long. And also, this is where if we are dealing with a very large amount of data, maybe we want to make sure that each row in the table doesn't take up too much space. And Sebastian, I'll share the link to that slide deck. And let me make sure I've got, yeah, my format here correct. And so there was a great point about the screening room schedule. This is getting ahead a little bit, but this is actually awesome. So this is kind of how we would do a screening room schedule. It's called a join table. let's see, we have a screening room. I'll just call it schedule because this actually, I think, will cover a lot of different things, which is interesting. So if I want to know like when a movie is playing and at what theater, what are the like critical pieces of information we need?
Time,
Time.
showtime.
Yep, I like it. Showtime and let's see, Postgres date types. There's a bunch of different date types. A good rule of thumb with Postgres is to keep it simple, to be honest. And with date types is to keep it simple. And it's actually not uncommon to use strings for dates in a database. A database server will have its own time zone set. So that can be a challenge. But let's just use date time. And SQL lets us say things like the showtime column has to exist when we create a new schedule event. Like we can't create a showing that has no time. Showtime and Icarus, thank you. And what else? What else do we need to know?
The title of the movie.
Yep, we need to know the movie. And that is actually going to be, this is where it's going to be interesting. I'm just going to do movie ID and integer for the moment. I'm going to make a note to do, make foreign key. And then I'll throw in the last one, which is we need to know the screening room that this is happening at. And we need to make our other tables here. We've got a schedule. And in fact, what I'm going to do is I'm going to pop over to, we'll make a new Google Sheet. I'm going to copy and paste this over here and it's going to be a mess, but I just kind of want to get this going so I can remember this. So we've got a movie, right? And a movie has an ID. A movie has the title. And let's just get that started over there. And then we have a screening room. And that has an ID. That has number of seats. That has a name. That has handicapped accessible. That has screen type. And I'll just very quickly like kind of make these bordered so it's a bit easier for us to see what's going on. And then we have the schedule. And I highly recommend, like when you're doing schema design, database design, start like this with a spreadsheet or on paper. Don't start writing SQL. Write out the tables and the columns and their relationships, because that's half the battle. So we've got showtime, we've got movie ID, we've got screening room ID. So then we have these three tables and these three relationships. And I also wanted to put this out here because it helps me keep track of things a bit. Yeah, you totally can build a database in Excel. Excel probably is a database in some sense. It's like an extremely powerful tool. SQL is actually a much nicer way to do it. So this is the high level of what we've got. A movie table, a screening room table, and a schedule table. And the schedule connects the movie and the screening room together with the time. So I do need to add create table movie. And what did we said? ID, integer, name, and text is also a field. And in fact, I should. So IDs are so important in the world of relational databases that they have their own term, the primary key. And think like we talk about like key and value with the dictionary, same idea. The primary key is a unique ID that you can use to get a row of data from a table. So here, what's the name of a movie that's out or was out or existed at some point in time?
Top Gun.
Top Gun. Top Gun Maverick. And then we've got Top Gun because they're showing it too for the release of Top Gun Maverick. So this is the primary key on the movie table that gets us that information. And so the screening room 1 has 100 seats. It's the main room. It is handicapped accessible. Screen type. What's a screen type? What are we talking about? Like Dolby?
Like
IMAX.
IMAX 3D. I don't know.
IMAX.
Yeah, 2D, 3D and IMAX at least.
Okay, I love it. IMAX, 2D. This is a great theater. All theaters are handicapped accessible. This one, we should probably rename it to like IMAX room. Just, we'll just call this main room. 100 seems way too small. It's probably more like 500, 100, 2. So showtime, I think Top Gun Maverick has to be playing at the IMAX. So ID 1, because that's the primary key for Top Gun. And then the screening room ID is also 1. And what's a good showtime for Top Gun Maverick at the IMAX?
7 p.m.
Yeah, I love it. We're not going to worry too much about the date time format. I'm just going to make it look something like this. We'll use 24-hour time. And then let's say there's a showing at 7 p.m. every day this week. So it's going to look something like that. And so on. And this is why doing some visual layout of your tables and your database schema is so powerful before sitting down and writing the SQL. And I think we have most everything we need. I do want to write proper SQL, and so we should indicate our primary keys. The caps are it's all just convention, by the way. None of this will break. But it does make it a bit easier to read like variable types and stuff. And then here it's a little trickier. So a foreign key, kind of like the name implies, is a column or group of columns that reference the primary key of another table. And the syntax is a little different here. So I think to do this for let's see, for movie ID, it would probably look something like, let me find a good example. Because I always, when I'm not doing this all day, I have to go and look it up. Here we go. This is probably the easiest way to do it. There's like 3 different ways to do it in Postgres. And I think I'll start with this one. So the movie ID references the movie table. And that's actually a good point. I want to say it is convention to make table names be plural, because it does make it a bit more readable and it is a bit more accurate. Like this table represents like screening rooms. And then over here, we're going to do the same thing. References, screening rooms. And so here, again, this is one of the great things about using like a database program like Postgres. Our database program figures out, hey, references says this is a foreign key. Let me go look at the schema for this other table and see what the primary key is, and Postgres will make that connection for us. There's a couple, again, if you look at this Stack Overflow post, you can specify that more explicitly. The term is a constraint, and sometimes you need to do that, but there's no one right way. Each approach has its use case. So honestly, I'm kind of going with references because it's very straightforward to read, and I think communicates intent. Yeah, so we're just kind of cooking. What else should we throw in here? Let's create another table for our movie database, and we can maybe model it if we want, and then we can throw it in the schema. And in fact, let me go ahead and rename this file, because it's really, this is not about screening rooms anymore. This is the schema for our database. So like we could in theory run this SQL file, give it to Postgres, and Postgres will create that database.
Adam, I have a question, and
Yes, sir.
I know a little bit about SQL, and I know that there are a lot of ways to do it wrong and less than efficiently. Will there be conversation about properly structuring a holistic database?
Can you talk a little bit more about what you mean?
Well, again, I know a little bit about database normalization.
Yeah.
To have tables not conflict with each other and have referential integrity. And then I guess it kind of goes back to the idea of, we talk about microservices at all, and how to properly structure these things so that you're minimizing connections and making things simple and extensible for the future.
Yeah, that's a great question. Let me move backwards through those points. So microservices are a way of architecting your entire web application. I don't know if I can find, I have too many tabs open. So I can't find the one that I want to that shows like the load balancing sort of. But so microservices, like a microservice architecture is going to operate. That is a nice diagram though. Like microservices, you're going to want to start thinking about the whole system, and then you may or may not use a relational database if you're creating a microservice. I think it is kind of common to use NoSQL databases with microservices, but that's outside the scope of kind of what we're looking at. And also, you don't necessarily want to, there's not like a one right way in terms of how you use a database with any particular overall architecture. Postgres itself has some pretty powerful features that kind of do some of what like NoSQL databases do. So you could potentially use Postgres in a microservice architecture. It would just depend on the specifics of the architecture itself.
Well, and
yeah.
So my thought is, how do we learn how to build a structure that doesn't get damaged when other components don't get damaged when one component changes?
Right. That's a great question. And you asked a couple of good questions in that vein about normalization, referential integrity. And actually, I think that's probably a good point to talk about. Actually, I didn't mean to jump here, but this is actually a great place to talk about some of specific things that we can do. Stepping back a little bit to answer your question at a higher level. Right now, I think those higher level concerns around designing a database schema are less relevant because we are going to focus more on the mechanics of like, how do I construct a database? And there are enough moving parts with that where doing that is a non-trivial task, especially when we mix it into Django. That said, you actually touch on something which is really good, that so there's an idea of what's called I don't know if it's a constraint per se. Yeah, it's part of a constraint. Like a foreign key is sort of called a constraint. And because what we can also specify is what happens when something gets deleted. And in fact, I think, let me go to our example, and I'm going to rewrite it in this fashion. So let's see, foreign key, we give it the column, references, parent column. I need a good example. Here we go. I'm going to steal this code and use it as some guide code real quick. And let's change this for the movie ID. I think that's a good one. And I'll put the movie ID here. So let's do this. Constraint, schedule, movie. Let me make sure I'm doing this correctly. Create table, constraints, like foreign key tests. Yeah, okay, so foreign key, schedule, movies, foreign key, movie, ID, references, movies. Probably they just, let's see how they do it here. Okay, yeah. Actually, this is a really good, yeah, that's a great question, Jim. So I can show two ways of creating foreign keys, and we can see some nice things that we can do. And then after this, we probably will pause and take a break so that when we come back, we can talk about querying, which is also important. And I'm just going to make sure that I have this right in terms of my commas and everything I want. Indentation doesn't matter. It's really for readability. So here are the two ways to create a foreign key constraint. We can use this references. I hesitate to call it a function, but that's maybe a feature of Postgres in particular. MySQL might not do it quite this way. We can also declare a constraint, and we're creating this column on our table. We're going to name it foreign key schedules movies. We're saying this constraint is a foreign key. It references this table movies, and the primary key that we're referencing is ID. So for some reason, if I didn't want to reference the primary key of the movie table, I could give it a different column on there, but we usually don't want to do that. And then to go back to your point, Jim, maybe we want to say, what happens when a movie gets deleted? Like if for some reason, like the Top Gun gets deleted from the movies, what should happen to our schedule? And I think this is what you were asking too about like referential integrity. So stepping back and not worrying about the code at all, like if I've got Top Gun playing in 3 theaters should I just be able to go and delete Top Gun as a movie from my database?
You said delete it?
Yeah,
No.
yeah, I would concur. And to go to the example, like, here's our schedule, here's our actual data. We've got Top Gun Maverick scheduled and playing in these screening rooms. Like, should the database allow me to just go and delete this row from the movie column?
So
And I
that's,
think,
that's kind of my point, is that I know that it's important that when we delete something, we don't want to wreck something else. I don't fully know or have the experience to properly design this so that you can
Yep.
expand it, but that you can isolate things and insulate them from troubles in the
Yeah.
future.
exactly. And it's honestly a two-step process, because just deciding without even thinking about how do we write the SQL to implement this, just deciding how this stuff should work is trickier than it seems. I think the movie example is pretty straightforward. Like, we can decide, hey, if we have a movie scheduled to play, we shouldn't just be able to delete that movie from the database. You know, but we should be able to delete a schedule whenever we want. And, you know, especially because a movie and a theater is a physical space, like for a video rental store, it might be a little different. And so Postgres has what are called constraints, and that's what we can use to enforce all these kinds of different rules. And in particular, when we create a foreign key, we can create constraints that help us, exactly like you were saying, maintain referential integrity. There shouldn't be a schedule for a movie that doesn't exist. And to be honest, we shouldn't be able to just delete a movie from the database if it's scheduled to play. And to be honest, I always have to kind of like Google the specific rules if I'm not doing it all the time. And it's this on delete rule. And I think this is, and reading through the docs, it looks like restrict is what we want. And I'll make this a bit bigger. That's really big. And I'll just read this out loud. Restricting and cascading deletes are the two most common options. Restrict prevents deletion of a referenced row. So we've got this screening room, or sorry, we've got this schedule. This foreign key here references this row movie, and restrict prevents the deletion of a referenced row. So it should look probably, I might not have the syntax there quite correct, but it would look like this. And it prevents a movie from being deleted if it's scheduled to play. And Jim, that was a great question about referential integrity. And these kinds of foreign key constraints are our go-to tools for managing this. And the syntax takes a little time to learn, but I think the important thing is really the concept and starting to get more comfortable with the concept. So are there any other restrictions or constraints that we should maybe create, as long as we're talking about constraints with our database schema that we have at the moment?
Here's one that might be a bit more advanced than we are currently set up for, but if
Yeah, go for
a
it.
screening room is under construction, no movies can be assigned to it on the
I like
schedule.
it. Yeah, that's a good one. That might be a bit advanced.
Or maybe a
But-
schedulable field, a binary or Boolean schedulable.
Yeah, I agree. Schedulable. How do you feel about available? Or this is where naming starts to become like people end up having strong feelings about naming. And actually, let's set a default value for that. Because maybe we want, when we create a new schedulable, when we create a new screening room, maybe we don't want it to be available because if it's just been added to the system, maybe it needs to be tested or cleaned or something. And I misspelled schedulable. I'm going to go with available because I can spell it better. Though I have to say, schedulable is really nice because the word does tie to schedules. So let me stop bike shedding there. So that's awesome. Let's check about Postgres on creation constraint. Because this is about when we add a new row to the database. And to be honest, Icarus, this is probably something that you would handle in the code calling the database. There is definitely a way to do this in SQL, and I think actually Postgres insert row constraint. So there's definitely a way to do this in SQL. You can even create custom functions in SQL. What ends up happening a lot of time is that as powerful as a database program is, as powerful as Postgres is, it's like the heart of the whole operation. So a lot of the times you don't want to put too much logic there. And also, honestly, the SQL files are harder for programmers to read. They're not modified as much. There are a lot of practical concerns that end up happening. And like if a screening room should, like if I should be able to create a schedule for a screening room that's not available, like that might be handled in the Python code, like in a level up. There could also be a situation where maybe you have a special screening or a test screening, and maybe this schedulable variable is more about if it's available for the general public. So I know that answers, yeah, it's naming things is hard, Gabo. I just saw your comment in the chat. There probably is a way to do that, and I need to look it up, but that's also actually a pretty good example of something you might move into the Python code, because you still will see a lot of developers, like if it starts to get too complicated, they might shift it out of the SQL. And I'll do a bit of Google because that's a great question. But I think now is probably a good pausing point. We don't have a ton more in our slide deck. We've talked about column types. We've seen column types. You can modify a schema, which I should mention. There's actually a command line interface for Postgres. And actually, as to your point, Icarus, changing a database schema is a tricky, complex operation, especially when you have a lot of real data and the database is being used. And it can require like coordinating with code changes or a lot of other things. So database schema design is one area where it's a little harder just to change stuff. And for that reason too, sometimes if logic is more complex, we might not want to put it in the schema, because if the logic is complex, there's a good chance that it will change. The rest of this is a little less relevant. And now is probably a good point to pause. Before we take a break, let's take like a 15-minute break so we can really refresh ourselves. Do people have any questions? How are people feeling? Good, so-so? So-so. Yeah, I think it'll be a lot friendlier once you start doing it. I've been talking about a lot of high-level stuff too. SQL is actually like a pretty straightforward language to work with. The syntax can be a bit of a pain, but it's actually not too bad.
When
Yes, sir, Ben.
yeah, when you're like on a team and it comes to like designing the schema and everything, like how much input is coming from team members versus just you developing the schema?
Yeah, that's a great question. That's a really good question. It will depend on the size of the team and the project. As a junior developer, so first of all, most of the time we will be working on an existing code base. So there's already an existing database. As a junior developer, you would probably be getting any changes to the database schema that you make like approved by other people, which you would with all your code anyway. It's pretty uncommon to like write a whole schema from scratch. We're going to learn about a bunch of tools for kind of managing that. If you're at a very large company, your software development team may not be able to touch the database schema at all. And the entire database, like think about the database that holds payroll for a large corporation. Your team might write a bunch of software that talks to that database server and makes queries to get the information you want. But the chances are that like changing the actual schema of the database, like handling payroll, or with the movie example, what's a movie theater chain? What's the name of a chain? My brain
AMC?
is, thank you.
AMC.
Yeah, let's say AMC has one awesome database that stores everything about all their theaters all across the country. And you're a team at AMC and you're working on the web app to display that information. There's probably a different team that handles that database and some backend code around it because that each of those are such big tasks. So your team would have like read access and write access to the database, but you probably would not have like access to the source code for the SQL schema for their Postgres database. So you might be writing a web app that uses that database as a service, but you're not working with the schema yourself. But you still might have to really understand it. And then maybe sometimes there's a feature that you need, and then you have to talk with the backend team and work together to like design the schema change, and that could be a whole thing. So the short answer is it really depends. And is that helpful, Ben? And does that, I'm not sure if you had like something in particular in mind too that would be helpful to talk about more.
No, I was just curious how much of, the responsibility is on the developers versus taking input from other people on the team. And yeah, that's all.
Yeah, great question. Great point about responsibility. I will say that as software developers, we do have a lot of responsibility in this area. That's part of what people sort of rely on us for. Again, though, as a junior software engineer, if the company knows what it's doing, you are not going to have all of that responsibility on your shoulders. You would maybe have like a piece of it, and that's part of really what you learn on the job. Louis, I saw you had your hand up. Yes, sir.
Yeah, I just wanted to ask about the keys and like, because I think I missed that part. Can you talk about the keys and like why, like how'd you do it and everything?
Yeah, totally. Great question. So let's see, that's not the one I want. So we've got these three databases, or we have three tables. Sorry, let me slow down. A movie table, a screening room table, a schedule table. The movie table has two columns, ID and title. The ID column is special because we are telling our database, this ID is how you uniquely identify any row. You know, maybe there's like a release date. Maybe there's a rating. And then when we have another table in our database, like the schedule where we want to like grab information from different places, like Jim, you were raising this point, like we could create a schedule table and we could copy all the information about each movie and the screening room into here, but then we would have tons of duplicate data all over the place. And not only would it take up more space, but then whenever we wanted to change anything, like maybe I'm the programmer who added Top Gun Maverick to the system and I made a typo. It's much easier if we only have to make that fix in one place. So relational databases are all about creating relationships between tables with, we call them references. And the main tool we use to do that is primary keys. So like right here, movie ID, this points to the primary key of the movie table for the movie that we care about for this schedule. Similarly, this screening room ID points to the primary key of the row of screening room data that we care about. And then when we are creating a table, we need to tell Postgres what the primary key is for that table, and that's like the unique ID. And then a foreign key is a way that we can have tables connect to each other. Is that helpful a little bit?
Yeah, just a little bit though. So where do you put, where do you make the key and where do you call the key? Like, how
Yeah.
do you making the key?
Yeah, great question. When you create a table, like this is all code that we can like run in Postgres. I could also do this one at a time, but like you can also put it in a file. So like this is the SQL code that creates a table named movies, and these are the different columns. Right now, this ID column or ID field, we know that we want to use it to like uniquely identify each movie, but Postgres doesn't know that right now. It's just another field that happens to be an integer.
Okay, so
So
you
by
just put the
adding-
primary key next to the ID?
Exactly,
Okay,
exactly. And this could be, you know, you could also make it text if you wanted to. Like, and actually that makes sense. Like you wouldn't, for a user, this wouldn't actually be the way that you want to do it, but like every user needs to have a unique email, right? And being able to look up a user by their email might be kind of nice. So we could make this a primary key if we wanted. A primary key doesn't have to be an integer, but it almost always is because this ends up having some other problems. Like we would actually probably do something like this, where it is still an integer and it's a primary key. And then this is has a unique constraint so that we say that like you can't enter two users that have the same email. But yeah, we just add primary key like next to whichever column we want to be the primary key, which is almost always going to be named ID and is almost always going to be an integer. And the database actually takes care of like incrementing the integer. Like the database will make sure that the ID is 2 and 3 and 4, and it won't allow like duplicate values in here.
and can you go to the schedule on the code? Like I want to see how you called it.
Yeah, totally. So we create the table. The show time is just the time that it happens. And then the magic is really, we have this column here that references this other table, screening rooms. And in this case, we're using a nice feature of Postgres that does a little bit of work for us, but to write out all the steps very explicitly, we saw this here where if we want to create like a foreign key that points to the movie. And in fact, this is not a great name. I should just name this like movie. FK is short for foreign key. And we're saying, hey, Postgres, reference the movie table, create a column on our schedules table, name it like movie ID, and point it to the ID of the movies table. And I think
Okay.
too, like this is, yeah, great question.
Yeah,
And this,
that makes sense.
totally, yeah, great question. And I think too, like doing some of the exercises will help. Let's take 10. And then at 11:30, we'll look a bit more at like writing SQL queries to get data. Cool. Thank you, folks.